Well, it's great always to have Sumit with us, and thank you for coming this time as well, despite the guest house fracas.
This place cannot get rid of me.
No, thank you. And of course, as many of you know, 2D string theory has been an abiding interest of Shumit's. Some of his most influential work in the subject was done while he was here, and I'm glad that he's returning to it today in this talk. Thanks, Shumit.
Right. So I returned to this after a long time. And it was sort of motivated by a couple of papers which addressed from the string theory point of view something about which I was interested in a long time. The first part of this talk I gave with this Lodha thing, at which time I didn't quite understand what's going on. I think I have a slightly better understanding now. So the two papers I'll be talking about, this is our first paper with Sean Hamilton and Sinong Liu, and the second paper with also with Gautam Mandal last month. Let me start with some general observations. So low energy effective theories almost always, when you have a cosmological background, end up with space-like singularities in the past or in the future. And these are somewhat puzzling from the point of view of physics because taken literally, they sort of imply beginning or end of time, and that's not something which one's really comfortable about. So one might think that a proper UV complete theory somehow resolves these by replacing them with a more reasonable time evolution. So I should just make a remark that, of course, these are space-like singularities. So the resolution of this is not like resolving a time-like singularity, because space-like singularity is not a thing. So you can't place a thing there to resolve it. So what it really means is that in some complete version of the theory, is it true that time stops there, or is it true that you can go beyond that and see something more reasonable? So of course, this is a big issue. So we look at models. So we look at toy models where this kind of thing can be addressed to some extent. Not to my entire satisfaction, but to some extent. So for those of you who are young enough that you've never seen this, let me give you a quick survey of 1 + 1 dimensional bosonic string. This is actually the earliest example of gauge gravity duality, and earliest example of gauge gravity duality is open closed duality, but in sort of in its modern form. And the dual theory of this string is gauged quantum mechanics of a single n by n Hermitian matrix. So you have a Hermitian matrix, you have a quantum mechanics of that matrix, and I'll write down the action. And I'll also explain what is meant by gauged. So this dual theory, of course, is a 0 + 1 dimensional theory. And the reason I'm calling it holography, even though it's not holography in the sense of bulk boundary, but in the sense that this theory is dual to a 1 + 1 dimensional bosonic string. And so one might wonder, what does the space dimension emerge from? It emerges from the internal degrees of freedom, in particular from the space of eigenvalues of this matrix. And here are a set of references, some of them old, some of them new, which has references to the original.
If one is to read one of them, which is the most readable? Are some of the more recent ones more readable? Sorry.
I would do Klebanov, and for the more modern viewpoint, I think Martinek has a pretty good review of the stuff with deep names.
Sumit, you say it's not bulk boundary.
Yeah.
There was this story in the 2000s about D-branes and...
Yeah. It's not bulk boundary in the sense of ADS-CFT. It's the same kind of duality as D-branes, leading to a higher dimensional space-time, but it's not like that there is a holographic screen somewhere where you put that matrix
There's
model.
not a sense in which it's lives at the recoupling end.
You can somehow, but maybe. I mean, it could be the asymptotic region, but it's not in the sense of that you have some variables there and you have a bulk boundary map with some kernel. I mean, I think those things are a little bit different.
So it's not as if you have some degrees of freedom you define on the matrix side, which are then mapped using some map to bulk.
No. There is. It's a bit ad hoc because what happens on the matrix side, you define some natural set of variables, but then you have to give sort of a non-trivial map to map it to the sigma model variables. That's what I meant. And the sigma model provides a notion of space and time. The matrix model defines another notion of space and time, but those are non-trivially related. And as far as I know, there is no symmetry reason, or it's really like the real independent and like honest to goodness connection is between S matrices. I mean, there is S matrix which you calculate on the string theory side. There is an S matrix which you calculate on the matrix model side, and they.
Just one last question about that. One very natural observable from the field theory would be to put it on a circle and put a Polyakov loop.
Yeah, that's right.
And you would imagine that maps to a winding string that goes all the way to infinity. Has that been looked at? And that would make it precise, right? Because it would tell you where the winding string ends.
This is in Lorentzian time or Euclidean time? In Euclidean time,
yeah,
right?
We've got. Yeah. Okay, maybe the problem is that the cigar itself is not normalizable.
Yeah.
This discussion, but anyway, later.
Yeah.
I'll actually.
It's kind of a background. You can't create that cigar from anything else. So I'll make a comment about that. Anything else? Yes.
This one plus one the target space. What is the space? Is it alias to
No, it's not. I'll tell you what this is. It's flat space.
It's flat.
Flat space with a linear dilaton.
Oh.
Okay. So let me tell you about the string theory. This is the worldsheet action. It has two worldsheet fields. One I'll call T as a function of the worldsheet variable sigma and tau. This is the target space time. It comes with a negative sign in the action. And then there is a Liouville field, phi, also a function of the worldsheet coordinate sigma and tau, that comes with a plus sign. And so roughly speaking, this T is like time, phi is like space in target space. This is the usual dilaton coupling. I mean, this is the usual coupling to the worldsheet Ricci. And that's the standard Liouville term, which is necessary in the non-critical string. This theory is sort of remarkably simple in the sense that there's only one set of propagating degree of freedom. So what I mean by propagating degree of freedom are things which have waves, which can be quantized to get particles. And those are represented by vertex operators, which are like this. They create states in the target space, which are massless scalars. For historical reasons, it's called a massless tachyon. But we'll stick with that terminology. So there's two sets of this. One is an incoming massless scalar and other incoming massless scalar, which is moving towards the Liouville wall where this object is becoming order 1. And another one, which is an outgoing particle. This is not the entire BRST cohomology class. I mean, there are infinite tower of states, but they do not represent propagating particles. What they rather represents are kind of backgrounds. I mean, the analogy, I think, which is given, I think it's due to Polyakov, is the following. Suppose in ordinary QED, you fix a gauge like a Lorentz gauge, del mu A mu equal to 0, right? Okay. Now, a state with 0 momentum always satisfies that condition. Okay. And that is sort of like a static Coulomb field in QED. So there are analogs of those states at every level in string theory. The most famous one is actually a two-dimensional black hole. This has been some bane of contention for many, many years. And I think as far as we know, this is not a black hole which can really be created by something. This is this question of normalizable and non-normalizable modes. But this exists as a background. This is a kind of a super selection sector of the theory where you can take that background and do physics with that.
The Liouville potential is to minus infinity as far as definitely. So it's like unbounded from.
No, the potential is plus of this action.
This is Lorentzian.
This is the action, Lorentzian. So I think.
And I'm sorry, I should know some of this because I lived through this era, but I don't. Are these extra states, these discrete states or whatever, do they correspond to extra kinds of charges or no? I mean, is the black hole something you can't make from starting without because there's some charge it carries, or it's not that? It's more normalizable versus non-normalizable?
I think it's more like a normalizable versus non-normalizable.
So it's really a deformation like turning on a source. That
It's sort of like that.
Okay. All right.
There's this strange thing, right? Like, because it looks normalizable if you look at the metric.
Right.
That's why I'm asking the question. Yeah.
That's right.
But because the black hole has a state built on top of the cigar, because it's now a winding mode can shrink. That tells you if you think of it as built on the cigar, it's got condensates of winding. So you look at the winding mode. And there is this analysis that tells you that the winding mode that is turned, this first winding mode that's turned on, is normalizable for k greater than something.
Yes, that's right.
Non-normalizable for k less than something. But string theory works at a particular k because it's critical. And it's in the non-normalized. So, turning on this winding mode, which you don't see in geometry, is the non-normalized.
So that's a very That's a very good way of putting it. Okay. So the physics is basically there is a Liouville wall, a strong coupling region, and there are excitations, massless excitations coming in. Those excitations, as we will see very soon, are self-interacting. It's this interaction which becomes strong near the wall, and they come out. The 2 particles can come in, and 10 particles can come out because of the interaction. And this is the S matrix. You compute an S matrix. There is an asymptotic region. You compute the S matrix in using standard worldsheet methods.
How is the Liouville wall parameterized? How do you define the wall itself?
Well, I mean, what I'm calling the Liouville wall is qualitative when this thing becomes order 1. But of course, the calculation is a calculation. I mean, you just take this background and calculate vertex operator correlation.
So it's not a fixed thing.
It's not a fixed thing. I mean, it's a fuzzy thing.
And again, sorry for these remedial questions, but the dilaton is growing towards the wall, if I remember.
Yes.
And so the string is getting more strongly coupled, but is it that you have some grain and you can get away? You don't really have to do string theory in some non-perturbative way, summing loops. You can just say some kind of grain and boundary conditions. Is it more like that? Or
no, I don't think so. No, I don't think so. This is a really, it's a non-perturbative thing.
Interesting.
But of course, the relevant question is how big is the string coupling and what?
But
That's a parameter.
Oh, that's a parameter.
Yeah.
So you can keep it very weakly coupled.
Yeah, you can. Yeah, that's the regime in which this was first. I'll come to that.
Okay.
It will become a little bit clear about what that. This is a parameter which basically becomes a string coupling.
Okay.
Okay. So just for reference, which I'm not going to use this, there is a low energy effective action which contains a metric. This is the metric on target space, which is also 2-dimensional, a dilaton, and this massless tachyon with some potential. So as I said, a fair amount is known about this 1 + 1 dimensional string theory, both from the worldsheet perspective and from the string field theory perspective. I mean, the latter one mostly pushed by Ashok Sen not too long ago. The duality with the matrix model has been recently established to rather remarkable precision, even at some non-perturbative corrections. I think these are de-instanton corrections to these things, which is it's kind of an indication that this is right. And of course, not the full non-perturbative. Now, it turns out the time-dependent backgrounds, which I'll be talking about, has been in the market for quite a while. I mean, it's starting from 2000s. There were these papers of Alexandrov, Kazakov, and Kostov, and Strominger, and some of my own papers, which started exploring time-dependent backgrounds in the string theory. And people thought, okay, here is an example where you can treat time-dependent backgrounds, which are difficult to do in string theory. So maybe we can make some progress. However, most of these discussions were from the matrix model side, which I will also explain. It's recently the analogs of those backgrounds on the string theory side have been calculated by Chu and Kutasov last year. That's what revived my interest in this subject. Yeah.
Time-dependent background will mean that your wall is dependent.
Yeah, it's a moving Liouville one.
Target time.
Yeah, time is time. Yeah. Worldsheet is something. I mean, okay. And what we observed is that there are several classes. We discuss some very special kinds of time-dependent backgrounds. There's a parameter there in that class, which will become very clear soon. I'm just giving you a kind of a introduction, which leads to interesting S matrices. And as I said, time-dependent backgrounds are like moving Liouville walls. So it's sort of like a moving mirror. And if you bounce things off a moving mirror, it's very well known, this particle creation. You have an interesting spectrum reminiscent of Hawking radiation. And that's what you sort of calculated. But there are other classes which do not admit reasonable S matrix. If something funny happens, we will see what's the funny thing that happens. And we are sort of motivated in trying to understand these troublesome things where the worldsheet can say very little.
So sorry, I've heard a talk of yours, of course, before, but is it a little bit like in these moving mirrors, you can try to set up some analog of a black hole by if the moving mirror moves faster and faster.
Yeah, so these troublesome things when the moving mirror becomes spacer.
Okay, I see. That's what you explained.
Faster than the speed of light. Okay. So let me explain the dual matrix model. As I said, it's gauge quantum mechanics of a single n by n Hermitian matrix. So this is that matrix M. There is a gauge field ET, just one component. This coupling, inverse coupling here, which is basically n up to some numerical thing which denotes the non-linearities in the potential. And the gauge invariance is very simple. For example, I can choose a gauge where ET equal to 0. So you're left with the Gauss law. And all that the Gauss law says is that all the states are singlets under this SUN. It's a remaining gauge, freedom of constant unitary matrix transformations. And they have to be singular. They have to be singlets. The wave function is therefore a function of the eigenvalues. So in this gauge choice, you can replace this matrix by these eigenvalues. Of course, as is well known, going from the matrix to the eigenvalues costs a determinant. There is a Jacobian, famously called the van der Monde determinant. And the van der Monde determinant is the factor is something like this. And then this, of course, means that the measure in the inner product of wave functions is non-trivial. So it's useful to make things simple, to absorb one factor of this square into the wave function itself. And the effect of that is to make this new redefined wave function to be antisymmetric under interchange of lambda 1 and lambda 2. You don't have to do it if you're willing to stay with a very complicated Hamiltonian and very complicated method. Of course, these are non-relativistic fermions. Just look at the kinetic term here. You know, in terms of the lambda, this will be just lambda dot square. And non-relativistic particles has an exact formulation in terms of a second quantized action, which is useful to think about. So in this expression, psi is that second quantized field. You know, this is second quantized field which anti-commutes because these are fermions. And this is a very simple action of these fermions which are interacting with an external potential and no self-interactions. If you are interested in some other sector of the theory, for example, to that action you add a source term such that the Gauss law tells you that the states, say, you know, transform like adjoints of the SUN. What that would bring you is an analog of a centrifugal term in this in the action of the particles, and that will make the particles interact by two-body interactions. It's related something called Calogero-Sutherland model.
And sorry, the bulk description of that source term would be like turning on some boundary operator, that is turning on some non-normalizable mode.
I don't think in general one doesn't know what it means. For the adjoint, it turns out something called the long string, and this is the work of Mother Sena. It's a string which comes off from infinity
all the way down.
On the gauge theory side, you know, right? You're just adding that source.
Yes, it's adding that source. Right.
So it feels very natural to say that it's always related to some sort of string going.
Some sort of string, but which string? Yeah.
But it has to be an extended source of the boundary.
Right. Because
only time. So
you're changing the Gauss law by putting a Wilson line in time.
Yeah, so okay. So, as known from the time of Etos, if I have any kind of matrix model like this, I can draw the 't Feynman diagrams, namely the ribbon diagrams in large N, and these ribbon diagrams describe describe some discretization of a worldsheet. Okay. Now, in this case, as in many other cases of non-critical string theory, there is actually a critical limit of this theory where the average number of tiles which form that worldsheet diverges. And in this case, it diverges as a log. In other cases, it diverges as a power law with well-defined exponents. And the understanding of that limit, that critical limit, is actually quite simple in terms of the matrices. So we'll start with a nice well-defined matrix model. This is like a double well potential. Okay. And of course, I have some number of fermions. The number of fermions is just n. So therefore, the ground state, and I'll fill both these wells, the ground state is filled up to some Fermi level mu f. Okay. Now, as you can see, as the Fermi level moves towards the top of that potential, the energy spectrum becomes continuous. I mean, the gap between the different energy levels becomes small, and it almost becomes a continuous spectrum. At the same time, if I take a particle very close to this top and ask how much time does it take to reach this, the time diverges. So you have a non-compact, in this limit, you see the emergence of a kind of a non-compact direction, okay, which is defined by the time it takes for a particle to go from a particular location off to the points. Okay.
And that diverges logarithmically.
That diverges logarithmically. So because of this divergence, And at the same time, we can, of course, go through this connection of the two diagrams with the worldsheet and convince yourself is that what that corresponds to is a case where, as I said, the average number of tiles diverges. So therefore, the worldsheet also becomes a continuum. So that is the string theory limit, which is described by a continuum worldsheet.
And this extra direction is then a spatial direction.
It's a spatial direction. It's not quite the spatial direction of that low energy effective action, which I wrote down. Okay. Good.
Sure. So, sorry, one sort of general question, which please postpone if you think. When you study these lower dimensional matrix models, not matrix quantum mechanics, just matrix integration. Nowadays, it's become very popular to think of that matrix as the Hamiltonian.
That's right. Well, it was from the day of Wigner.
It was.
right, yeah.
Okay, here, matrices that are not the Hamiltonian.
It's not the Hamiltonian.
It's more like n equals 4.
Right.
Does the Hamiltonian play any role in this?
The Hamiltonian as a matrix, as an infinite dimensional matrix. Not that I'm aware of. I mean, I don't know. I mean, of course, what this Dyson and Wigner did is to represent systems with sort of chaotic spectrum by random matrices, right?
So maybe I can be a little more precise. There are these limits of minimal models that give you C equals 1.
That's right.
So if you take a limit, sequence
of a multi-matrix model, right?
Where you think of the interpretation, how do the interpretations match onto each other?
That's an interesting question. I don't know the answer to. Yeah, I mean, clearly this matrix quantum mechanics is a limit of a chain of infinite number of matrices. It's like multi-matrix integrals where the couplings between the two matrices are just like M1, M2 plus M2, M3 plus M3, M4 and so on. So maybe thinking of it that way might...
But also, I'm so sorry, there is this, Shiraz has asked me this many times. In Shankar Stanford's paper, the more recent developments, there is a section where they talk about these minimal kind of models, right? P, P something.
So it's a minimal string theory.
Yeah, and there's a connection between somehow, I think, taking a sequence of those models and the double scale limit they consider. And it's something I'd love to understand better, never done, but maybe that might connect to...
Yeah, that's one limit. There's another limit of these kind of models that goes to C equals 1.
That's right.
Yeah. So that's what you're saying, right? So then it would be nice to connect that.
That would indeed be very nice.
You asked me. Yeah, I think we really should do that.
Yes.
So you are relating the matrix models with the string theory worldsheet.
So I think the string theory worldsheet connection comes like you have a matrix model, which is like Young-Mills theory, and you have diagrams in that Young-Mills theory. Those diagrams form a kind of a discretization of a two-dimensional surface. The large N expansion is a topological expansion of that. So this is like 't Hooft's identification. They're saying that, okay, 't Hooft asked the question like QCD is a theory of strings, but if it is a theory of strings, what is the string coupling? Because otherwise it doesn't make sense to talk about a string. So he invented a coupling, which is 1 upon n. So it is basically in that spirit.
Okay, so from discrete to continuous, it is becoming in that spirit. But what this tau and sigma, which represents this worldsheet,
right?
What are the analog of them? Is it like T and phi, which is being...
No. Tau and sigma are like this is a diagram, for example. This is a Feynman diagram, say. Okay, so these are the vertices of this diagram. So these diagrams you think of as the points on a two-dimensional worldsheet. Okay, and these are little tiles on the two-dimensional worldsheet. That worldsheet is parameterized by tau and sigma. Okay. Phi and T are fields which are living here. Okay, and the propagator, which of the matrix thing, is basically in this simple case that exponential of grad t square plus grad sigma square. That's roughly the direction.
Sorry, just one question, which is, since it's non-interacting fermions, right?
Right.
It's unlikely to be a chaotic model. Right?
No, it is certainly not. It's an integrated one. We'll see the consequence of that. Yeah.
And Sumit, away from this double scaling limit, presumably the string theory is some discrete object.
Yeah, we'll.
That also, is there some sense in which?
Well, I don't know. That will be the last few slides of my talk. So we'll come to that section. We'll see that we get forced into that. Yeah. Yeah.
What is analog of this E potential U of lambda on the worldsheet side? Is it the tachyon, sorry, the potential that is generated by the dilaton?
No. That's a very different thing. So that potential is the one which causes these Feynman diagrams.
And on the worldsheet, what is it?
There are parameters in that potential. For example, if I have like a quartic potential, so that parameter gets indirectly sort of related to the cosmological constant on the worldsheet. See, from the point of view of the matrix model or the gauge theory, there's a coupling constant sitting here everywhere, right? So let's call this coupling constant kappa. In my notation, this is basically n upon b. It's some object. And so this diagram will have this coupling constant raised to number of vertices. Okay. The number of vertices is roughly the area of the worldsheet. So this is like, log of this object is like the worldsheet cosmological constant. That was that mu which I wrote in terms of the Liouville potential. So that's like the interpretation.
Sorry, I have a related question. Why can't we directly started with the inverse harmonic oscillator potential?
We will see what happens. I mean, I'll for a lot of time we'll do the inverse harmonic oscillator and we will see what happens. Okay, so hold on for a few minutes. Okay. Yeah. So I want to start with something safe. So this is something safe. So let's start here. Okay. Good. Because of this, the normal thing which one does is to zoom onto this top of that potential so that this potential just becomes an inverted oscillator potential, and just then one is happy and solves the problem. It's potential. So the technical rescaling which does that is by this. Beta, remember, is an object which is proportional to n. It's n up to this some number kappa. So beta is of order n. And what GS is something which is sort of held fixed. So this is roughly speaking this object. No, not roughly, precisely speaking this object. In the original potential, there is a Fermi level which I denote by minus mu f. So you take mu f going to 0, you take beta going to infinity, keeping this object fit, and that is that parameter.
So you can make it weakly coupled, everything nicely under control.
Right.
And can you, just out of curiosity, also solve enough about the matrix model at strong coupling then? I mean, just to see how the behavior changes, presumably? No.
Yeah, from the Fermion theory, you can, in principle. Yeah. I mean, Fermion is a free theory.
Just because when you do particle production or nonlinear.
Yeah, but there's, that translation becomes a little bit. That's all. Yeah. Good. I mean, there are exact correlation functions you can write with. You want this paper of Moore and Gibbs-Park, I think, which reviews all that old stuff. Okay. So just to explain why you are left with an inverted oscillator is that if you do this, plug it into the Schrodinger equation, you see that this term is sort of suppressed compared to that term in that limit where beta times by order beta times GS. So in a limit where GS is held fixed and beta is taken to infinity, we cross out this. Okay. when you have a large number of fermions, there is a well-known approximation in atomic physics, which is called the Thomas-Fermi approximation. So you would imagine that having a large number of fermions means that in some sense the theory is classical. On the other hand, these are fermions, so there has to be Pauli exclusion principle. So what Thomas and Fermi did was to say, well, I'll treat it sort of like a classical system and write down a phase space density which has the property that the phase space density is either 0 or 1. So that's the Pauli principle. Okay. So as a result, any state of that system, so the phase space density is precisely the expectation value of this operator in some state. This operator, I mean, it's like the Wigner phase space operator, except that it sort of imposes an additional condition that it's actually 0 or 1. Okay. Never mind, given the equations of motion for psi, you can derive what is the equation of motion for u. And as you would expect, it becomes like an Euler equation. Okay. It's like a fluid. So a state of the system is conventionally represented as a filled region in phase space. So what I have done, I should have actually drawn that blue thing over here as well. This is the single particle phase space. Okay. So in the single particle phase space, the n particles are represented by orbits. These are inverted oscillator potentials. The orbits are all hyperbola. Okay. So this picture means that all the orbits, below this, this orbit and that orbit, they're all filled. So this is like an example of a ground state of that system. This object is related to the Fermi level. I mean, we have rescaled things, so the Fermi level is chosen to be half or something.
Sorry, but in the first line, it's a little bit like the Wigner distribution,
Right.
But except for psi dagger sign.
Yes.
The density of fermions.
Except that it's a kind of Fourier transform of a split object.
Of a split object, yeah. Like in the Wigner, right?
It's like in the Wigner.
Yeah. So you're thinking of the density as a function both of position and number.
Not the density really. Okay. No. It's not the density. I mean, they're really like a P and an X. So this is like, it's like a, I mean, if you take the expectation value, it's like a correlation function of fermions, which are separated by a distance y. Okay. X is like the center of mass, and you're integrating over y. You're taking a Fourier transform with respect to y by this e to the I px.
Perhaps Sandeep said that in the one particle state, this would be exactly like the Wigner function for that one particle wave.
Yes, that's right.
Yeah.
Yes.
It's an attempt to capture the fact that the electron can be there's a density for electrons at some location with some momentum, right?
Yes.
It's an attempt to capture that.
That's right, it's captured.
Yeah. Okay. Go ahead.
Well, so this is the ground state. I did it wrong. I mean, this blue, you should cover that part also as blue just for safety, because otherwise things will just tunnel to the other end. So let's do that. Not play much of a role here. An excited state would be taken by some bunch of fermions, which you take from below the Fermi sea and put above. So there are some fermions you have taken, and so this is like an undulation like this. And of course, this is these are non-relativistic fermions. So the higher up have higher velocities. So there is a dispersion. I mean, the group velocity is not the same as the phase velocity, and that causes interesting things to happen, as we will see. And so if you have an excitation like this at some time, each point here travels along its own hyperbola. So the whole blob will get deformed and travel back. That is the scattering. That deformation can be sort of rewritten in a way to have a particle interpretation, as we will see later on. A beautiful work by Polchinski in those days. Okay, so this is like the scattering. So we calculate that scattering. Now, there's a useful way of thinking about these deformations of the Fermi sea is to think of really the density of fermions, which is like psi dagger psi. So psi dagger psi, you represent it as a boson, as a x derivative of some field phi. It's called the collective field. So this, in terms in this Thomas Fermi, the density is like the integral of u over momentum. The momentum density of the bosonic field is the integral of u with an extra factor of p inserted there over momentum. Okay. So this pi phi is a canonically conjugate variable to phi. And if I start from the matrix, this object is after sum of delta functions, and that sum of delta functions you can compactly write as a trace of delta function of f x. And in the large n limit, you can actually write down what the Hamiltonian of this thing is. You start with the Hamiltonian of the matrix model, make this change of variables, you obtain a new Hamiltonian, and this is the form of the Hamiltonian. There are order 1 upon n terms, which I have not written down. They do play an important role in the game, but this is good enough for the physics. So notice this field phi is an interacting field. I mean, to this order, it's a cubic interaction. And the cause of this interaction is the non-relativistic nature of the fermions. Suppose these were like usual chiral fermions. Chiral fermions bosonize to chiral bosons, which are also free. And the reason why these are not free is because these are non-relativistic, and the group velocity is not the same as the phase velocity. Okay, so this represents this thing, and see, all these things are contained in this Thomas Fermi. I mean, they have analogs of 1930s or something like that. There's an additional term which I have added, and this has two parts. One is this potential x square. There's it is x square psi dagger psi, so that's where this comes from. The other one is to go from, if you wish, a microcanonical fixed energy description to a canonical description in terms of a chemical potential. And I've rescaled things to put that chemical potential to be half. Okay.
Is the action, the Hamiltonian seems local in X?
Mm-hmm.
Is that just a leading order in N, or is it actually local?
No, it is leading order in N. Right. Okay. But even that is a little bit sort of surprising. I mean, even leading order in N, I mean, that you have a local thing. Okay? Just as a warning, this X is not the sigma model spatial direction. I mean, there's a non-trivial map there.
From the viewpoint of the Thomas Fermi, you're just making these bumps and following them.
Mm-hmm.
But from that viewpoint, would you allow for configurations which had a gap somewhere in the middle and so on?
If you start with a state like that, so that's like an excited state where you have a gap in the middle, and if you have a blob there, they are sort of like classical D-branes. These fermions are like unstable D-branes in the theory. So if you have a whole bunch of them like that, so they would be sort of like that, I think.
But in the manipulation that takes you from there to there,
Mm-hmm.
you're assuming there's no such things.
Yes, that's right. Absolutely right. Yeah. Okay. So the first thing you think about the physics of this model, treat it like a garden variety Hamiltonian. I have a Hamiltonian with a field and its canonical conjugate, do physics as you always do. GS is a number at your will, so you choose it to be small. So if you choose that to be small, that's clearly the coupling constant. You see the way GS appears in the kinetic term as well as the potential term. So you choose to be small. So what do? I mean, you first find a classical solution, the lowest energy classical solution. So the lowest energy classical solution is time independent, and that is this. This is the description of the Fermi sea of the ground state. And then what would you do? You would expand around that classical solution like that and write down the action for the fluctuation. And then the game is to do Feynman diagrams with that, basically. Okay. So the thing to note is, if you do that, I have done two things. I have gone from this x to a new coordinate, which I call cos q. If you think about this, q happens to be the time of flight coordinate. It's sort of convenient because in these coordinates, the kinetic term of that action just becomes like that of a bit Koskian. And this will sort of play a role in trying to interpret, the space-time. So T and Q are, roughly speaking, some notion of space-time. T is the original matrix model time. Q is this thing which is invented from the space of eigenvalues. And nicely, the kinetic term for this fluctuation is quite standard massless scalar. Okay. It's no big deal about it. It is very well known. Small excitations about a Fermi surface are massless objects. It's a linear dispersion relation. This is slightly of a bigger deal. It's saying that there is a sort of approximately local interaction of these things. The interactions are dependent on Q, so this is not translationally invariant. There was no reason to begin with that it should be. There was a potential after all, so it's not translationally invariant. So, but the thing is that this is the coupling of the fluctuations. This grows large near Q equal to 0. And the Q equal to 0 is like X equal to 1. And because of these rescalings, that's like the place, this place. That's where the things turn up. At X, by choice, this is X equal to 1. So that's like a wall in this language. And the scattering from this wall, this is what, you can three calculations you do. One calculation you do from fermions, second calculation you do from here using Feynman diagrams, and then a third calculation which you do from string theory, and they are all in pretty good agreement. I don't know to how many limits, but yeah.
How do you relate P and Q to I thought those were things in the matrix gauge quantum mechanics, right?
T was the time of quantum mechanics.
And Q was also related to the matrix quantum mechanics.
Yeah, so that's X was the space of eigenvalues.
And now you're relating this to the target space-time coordinates.
Okay, not quite. There is a story there. Maybe I'll explain to you privately. The story is that there's actually a non-local kernel which relates this field eta to that massless tachyon. The scale of that non-locality is the string scale. Okay. And, there's an interpretation of that non-locality is that it sort of integrates out, all the higher stringy modes. It sort of encodes gravity. I mean, there's no dynamical gravity here, but there's a Coulombic part of the gravity. The interpretation of that is that it sort of encodes that gravitational interaction.
Okay, so the eta is somewhat related to the massless
tachyon. Yeah.
And that's how
up to a string scale fuzziness. Yeah.
Okay, and that's how this is connected to the targets.
Absolutely. Right. Okay. Time dependent backgrounds. So what do? You take the Liouville potential and you deform it by some vortex operators which explicit functions of time in it. Okay. Now, in this game, there is a one-to-one correspondence between those vortex operators and operators in the matrix model. In terms of operators which are made out of the matrix and the canonical conjugate to the matrix is a trace of pi plus m raised to the some power e to the something else. But this map is sort of known in this game. So in the matrix model, that also, I'll tell you in the matrix model what that corresponds to.
And this is exactly marginal in the same sense that phi e to the 2 phi. Something like that.
Something like that.
It's an okay thing to do on the worldsheet.
I'm not completely sure of that, but that's the way it is treated. Okay. Yeah. There's some integrability story of this, which this Kazakov and Kostov also found.
analytically continue time.
Yeah.
Then this becomes like a holomorphic operator. No.
Then it becomes like the kind of the.
I was thinking.
Then it becomes like a more conventional vertex operator.
Conventional, but not worse. Yeah.
Yeah.
Then it's more confusing than it's exactly.
Yeah.
That's right.
Yeah. I'm not completely sure of that. Okay.
Sorry, I was thinking it looks a little like holomorphic in space-time, right? Because
I understand because of this r times p minus pi. Yes.
And maybe that means that there cannot be singularities.
I see. Could be. When two of these vertex operators meet, yeah.
Because they have charge adds.
Yeah, sure. Probably. Yeah. Okay. So if I think of this potential being order 1 as a kind of a rough definition of the Liouville wall, this represents a moving Liouville wall. Okay. For R, R is this parameter I was talking about. So when R is less than 2, then phi going to minus infinity is still an asymptotic region. So there's a hope of defining some S matrix. So we'll stick to that. So what these people found is when R is less than 1, there is a well-defined S matrix, which includes particle production from the moving wall, and pretty much like Hawking of this kind of spectrum. And in this parameter, also, this wall remains subluminal at all times, remains time like that. At late times, the speed of the Liouville wall approaches this constant value, and as you would see that if we take r going to 1, this is the speed of light, and as it exceeds 1, this actually exceeds 1. There's nothing wrong with that, of course, because nothing physical is moving at speeds faster than the speed of light. All the physical excitations are massless phi. Because of that, if you throw in something before that thing comes back, the Liouville wall sort of overtakes you in a way. So you have an in asymptotic region, you don't have an out asymptotic region. So just the usual string theory things becomes a little bit more.
So the wall is, you have the recoupling region and the wall is moving towards it?
Towards
superluminal.
Yeah, superluminal. So by the time your particles are coming, but it catches up. Very good. So what is the description?
It's better than, when I was saying there is some way in which you can model black holes, you often take the wall to move away. So then you can't reflect and come back, right? And you get absorbed. Right. But it's not that. It's not that. Okay.
Right. At least for these parameters. These time-dependent backgrounds correspond to time-dependent Fermi surfaces, which look like this. And I should now qualify what do I mean by a time-dependent Fermi surfaces.
Can I ask a question?
Yes.
R-2 was not present in the time-independent action, right? It's here in time-dependent action. So
R was not there at all, right?
Yeah, in R-2 factor was not there.
No, there was no T also in the time independent thing. Is that what you meant?
So what does it changing on the figure you draw on the blackboard? On that figure, what's it changing?
This one, the Feynman diagram?
Yeah.
No, nothing is changing. The state is changing. I'll explain that. The theory is the same, but it's a different state of the theory. Okay.
Nice.
So that's the next step of trying to understand what does this actually mean. This comes, as I said, like there's a one-to-one correspondence between those vertex operators and operators in the matrix model, and that's how people write down this thing. So we would like to think of it in a slightly differently. We would like to think of this as the result of what I'll call a quantum quench. So let me try to explain what I mean. Imagine I start at t equal to 0 with a profile which is like this, which is this Okay, if I started at t equal to 0 with the profile which is x squared minus p squared equal to 1, that's like that hyperbola, at all times it is going to remain like that. That's the ground state, it's the energy eigenstate of the system. Okay? But I can excite the system. I'll draw some pictures pretty soon. I excite the systems such that this is what I start out. It's up to me. I start out with that kind of initial condition. Okay? If you wish, you can think of it as the ground state of a many-body Hamiltonian, which is a deformation of this Hamiltonian by this kind of term. You don't have to, but you can just think of it as an initial state.
So this is your initial Fermi surface.
This is the initial Fermi surface, and then every point evolves according to the standard Hamiltonian. Okay, and this is the standard double-scale Hamiltonian. These are the particle trajectories. If you plug these things back in here, you get that. And I'm only going to take lambda plus, which I take to be there. Good. So what do they look like? So here is an example of, I don't know why my collaborator took r equal to pi upon 4, but it's something which is less than 1. Okay. Very good. So it's like at t equal to 0, it's a little bit deformed Fermi surface. It doesn't look quite like the hyperbola. I mean, it's a little bit deformed. And if you take a point on that, see this point, and follow it, what happens at t equal to 1? This point reaches that point. And at t equal to 2, it reaches that point. At t equal to 3, it reaches that point. So you take the locus of all points on the Fermi surface according to their own hyperbola, and at a given time that creates a snapshot of what the filled region of the Fermi surface is. And in this approximation, a filled region of the Fermi surface is one-to-one correspond to a Thomas Fermi state. So as you can see, what is happening is that this edge is sort of moving away like that. Okay, so that's roughly the moving region one. Okay. For r less than 1, what do you find is?
How do you match equal time surfaces around the different black trajectory? Sumit, the arrowhead?
The arrow.
The arrow.
Yeah. Equal time.
Meaning like, so I take any one point and I go some distance. To create the snapshot, that's what I'm supposed to do.
I see. So at t equal to 0, the Fermi surface is this blue line.
Oh, the different green lines are the different colors are the different
times. Right.
I'm with you.
So you take every point on the blue line and evolve it in time. Okay.
So this
create
is the wall is moving.
Yeah, it's sort of telling you the wall is moving.
I got it. Yes.
Good. When r, again, I don't know why it was taken to be pi upon 2, but it's bigger than 1. Okay. And it's quite representative if you could play around with these things. I actually wrote this mathematical code from ChatGPT. Okay, I asked ChatGPT to write me a code which does this, and so that's what it is. And then you can see that something more drastic happens to that Fermi surface. There's a breakdown like this, and furthermore, something very funny happens because this is an inverted oscillator potential, which corresponds to that continuum limit on the worldsheet, which corresponds to an infinite line which has somehow evolved. So the fermions are getting pushed off, like all the fermions are pushed off all the way to infinity. Now that's not good, and we'll see that it will cause some pathologies of the theory, which we would like to understand.
And why are these fermions pushed off from this asymptote, not in some other way?
It has got to do with this fact that I've chosen this lambda plus to be negative. It turns out if you take lambda plus to be positive, something else happens, which I'll not discuss.
And so, Sumit, if I just look at that colored plot, the one after. So the blue line, let me say -1 is a time-like trajectory, is what I'm thinking, initial. I mean, the green is qualitatively different, right? It looks more space-like.
I mean, I know not time and space.
P and X.
No, it's P and X.
But I mean, somehow that seemed more like a wall which was which was, maybe I'm wrong, which was far from your weak coupling, but sort of some.
What you're saying will turn out to be right. And
Okay, and this seems like a wall which is going towards the.
it actually goes down and very, very far away. It sort of meets it at this point, intersects the x-axis here. Okay, sure. Okay, and this is for our greater than 2 or something that happens. Okay, so how do we understand this? So, the way we would like to understand this is that given this background, which is time dependent, we want to understand how physical excitations, physical particles move in this background. Okay. So a useful way of doing that is again to go to these bosonic variables, which is not an exact formulation, but it's good enough for this purpose. So what we want to do is exactly what we did around the ground state. You write down what is the classical solution of the collective field theory. This will be a time-dependent classical solution, and there is a definite way of how to, as I said, that it's like this object is the density of fermions, which is an integral of the fermion density. And if I have a Fermi surface which is like this, where all the interior regions are filled, if you do that integral over momenta, you'll get P plus minus P minus. So that object is in fact del x phi. Similarly, the momentum density will turn out to be an integral of P from P minus to P plus, which is P plus square minus P minus square. And I've assumed here that this portion of the Fermi surface is quadratic. What we mean by quadratic is that a constant x line cuts the surface only twice. But what happens when it is not, and we will be led into that, I'll come to later on. Okay. So the technology is known, so let's do that. So you find what this phi naught is using this dictionary, expand and obtain the quadratic action and the cubic action. Okay. Looks complicated, there's time dependence everywhere, but at the end of the day, it's a massless scalar field in 2 dimensions. Okay, and you can look at this quadratic action and immediately realize that it's an action of a massless scalar in a metric which is conformal to this metric, and it's a time dependent metric.
So if you just go back to the previous, why is it? Are there interaction terms, but you're suppressing them?
No, this is the interaction term. I've written the cubic interaction.
Okay. So it's
that's the quadratic term, and then there's the interaction term, and there are higher order interaction terms. Yes.
So why does this line intersect still only at 2 points, like it would have been that way?
Not necessary, but I'll start with that, and we will see what happens when it doesn't.
And this will be the ground state even in this time dependent.
It's a time dependent solution, so there's nothing like a ground state. It's some time dependent thing, non-trivial excited state. As I said, you started out with something which is not the ground state of the Hamiltonian, a many body state like that. So it evolves non-trivial in time. Good. Okay, so it's a massless scalar in a metric. It's in a 2-dimensional metric, which, in the way we just followed our nose and you land up with this metric. And of course, a 2-dimensional scalar, in 2 dimensions, every metric is conformal to the Minkowski metric. And the Minkowski metric is useful because if I'm able to make a coordinate transformation to go to this matrix, the physical excitations are just tau equal to plus minus q. Okay, so that will let me look at the global features of the space-time which has emerged. That's what I call the emergent global space-time.
Missing something. Where is R, your parameter?
R. So it is hidden in this del t of phi and del x. Del t of phi naught.
That was the initial
phi naught.
Yes. So phi naught is changing.
Yes. Okay. This change of variables to that is non-trivial. And for example, for the static solutions, I already had displayed that the tau was just the matrix model time, and the q was just related to this x by this transformation. And we haven't been able to do this exactly for all values of R. But just to give an example, I'll give you the result for R equal to 1 and R equal to 2 for which we could solve this problem exactly, analytically. But we find that R equal to 1, the Minkowskian time, I'll call this Minkowskian coordinates, tau and q, is the same as the matrix model time, but the Minkowskian space is a combination of the space and time, which is a signature of the fact that the initial thing was time dependent. For R equal to 2, something more drastic happens. There's a non-trivial transformation between the matrix model time and the Minkowskian time. In particular, when the matrix model time goes to infinity, this time tau approaches a finite limit. And you can calculate what happens to the couplings in that cubic term in that limit, and at least one of them always diverge. So what is happening this was just a crutch to understand the motion of physical excitations. So what we conclude is that starting with this excited initial state, you evolve into something where at late times, everywhere in space, the coupling becomes very strong. And that's for R equal to 2. But we are, of course, not interested in R. We are interested in the region between R and 1 and 2. So ChatGPT actually gave us a mathematical code to figure that thing out.
So sorry, when you say coupling, did you mean G string becomes strong or what?
G string is a number.
G string number.
But
the electron, I mean, is it because
these couplings, these are space-time dependent.
So the field is no longer well approximated as a
small perturbation around.
As just propagating freely.
That's right. Yeah.
Your phi naught is not necessarily your profile, right? It is more generally true.
This is more generally true.
In the metric.
Yeah. But when we calculate things, we use that particular profile.
Sumit,
Yes.
I suppose your R was telling you how the Fermi surface is. R is characterizing the Fermi surface.
Yes.
What is lambda plus and lambda minus characterizing?
They were lambda plus and lambda minus can be absorbed in a shift of time, because it's first lambda plus e to the RT. You shift R by log of T by log of lambda plus.
Okay.
So the only thing that's significant is the sign of lambda plus or lambda minus, and I've chosen a particular sign here.
And what is there something physical about this lambda plus and lambda minus on the space target space time state? What is it?
No, so as I said, the sign is physically significant, and they actually lead to very different kind of evolution of Fermi surfaces. I just took one thing because that's where the string theory calculations were done.
It should be just physically, I mean, if this wall is tearing down towards the boundary of decoupling, in any kind of local theory, nothing would come back, right? It hits, maybe changes the state of the wall. The wall is just coming.
Yeah, that's why we call it a space-like singularity. It's like going and hitting a strongly coupled region.
And then you just stick there because the region's moving towards
it.
Right?
Yeah.
It's slightly non-local, but still, I suppose.
Still, that's, I think, the physics. So let me sort of draw in terms of pictures what the space-time looks like. So what is drawn in this picture are equal matrix model time surfaces in this Minkowski diagram, where this is the Minkowski time tau, this is the Minkowski space q. The thing to remember, the physical excitations move at 45 degrees in this thing. So this is like an early matrix model time, slightly later, the whole thing sort of keeps moving up. And the Penrose diagram for this sort of looks like this. Okay. They eventually, at late times, they approach scribe plus and scribe minus. From one side, scribe plus, the left scribe plus, and right scribe plus.
So what's special about Q?
So the Q equal to 0 happened to be the place originally the place which was the hump of the potential. So that's the one which separates the two sides. So I've not taken into account non-perturbative tunneling effects. So that thing is like a hard wall.
I think I was. So you actually have two asymptotic regions, right? Because you have this.
For R less than 1.
You have this double hump.
Yeah.
But even for R greater than 1, you don't have that. Like the wall goes tearing off towards one of the two boundaries, right? If I'm right.
No, the solution is actually symmetric. This is a move like that.
It moves like that.
Like that. Yeah. Okay. Good. In contrast, this is what the space-time looks like in the region between 1 and 2. Okay? And again, all these different colors are different time slices drawn in this Minkowskian diagram. It's best shown in a Penrose diagram like this, and you find that at late times it asymptotes a space-like surface. It doesn't go all the way to spread plus. Yeah. And then you can calculate, so you can see that what is this space-like surface? It actually is that superluminal Liouville wall. Okay, and you can calculate.
Just sorry.
Yeah.
I mean, you had a picture in P and X where
Yeah.
you had some, and now you're saying, now you're saying in actual tau and Q.
Yes.
Also, you get a very similar.
Very similar, and a boundary, really a space-like boundary. Of course, a space-like boundary would be sort of disastrous if nothing was happening there. But it turns out that space-like boundary is like a singularity, because if you calculate these couplings, and you can calculate those couplings, what those couplings become at the space-like boundary, and what you find is that at least one of the couplings diverges there. So from the point of view of this effective field theory of the collective fields, it is like what a singularity is. This is a two-dimensional model, so there is no curvature, kind of things. And a singularity is denoted by a strongly coupled region. Good. So this appears as a space-like singularity in a semi-classical description. And in fact, at late times, it actually coincides with the Liouville wall. You can actually trace what the Liouville wall is, and you find that it is that Liouville wall which is actually becoming space-like.
So just to make sure I'm not losing the thread, the physical question then is I shoot some tachyons in from at very early time,
So it gets
and they go and they hit the wall, space-like, and now we want to know what happens.
We want to know what happens.
Sorry, can you contrast it with the R less than 1 case?
Yeah.
The image.
This is R less than 1.
Yes.
I mean, these surfaces, they asymptote to scrapplers.
And yes, and now what does it change the R?
They asymptote to.
Where's the boundary here? What do you call the boundary here?
This green and yellow thing is the locus of points at late matrix model times. So all excitations we sort of end up here. It's like a big crunch, if you wish. So we would like to know what is really going on here. I mean, can we figure out what is going on here? And the first thing to realize is that, and this is what we did in our recent paper, the first thing is to realize, is to try to understand why this is happening. This is actually happening because of a pathology of that model. Everything was done in an inverted oscillator potential, and the extent was infinite. The fermions were all being pushed away to infinity. Okay.
Infinity is the other
So it's like this. Potential was like that, right? And all the fermions sort of going off like
a
that.
reflection or whatever go off to
infinity.
Okay.
So they're sort of leaking out to infinity, and this can only happen because we have taken a limit where n is equal to infinity with g and L fixed. Okay. To see what really happens, we need to first go away from that limit and see what the picture is. So that's what we did. Then, of course, going away from the limit is not universal. I mean, it depends on how you modify that infrared wall. So we decided to modify it by something which is nice, which is like a quartic. I started writing with a quartic potential. So let's solve the problem in this quartic potential.
But in the earlier case, the quartic term was not there because of the limit.
Because of the limit. N going to infinity, GS held fixed.
But now you are purposely adding this term.
Right.
Not leave the fermions.
Right. We want to have a well-defined, well-posed problem and see what happens.
So the potential, of course, you could modify in whatever way you like. Is there some nice one which has a good bulk picture or something?
I don't know. I mean,
even for this modification, is it clear what?
We'll see what bulk picture we get. Okay. We'll first follow our nose and solve this problem. Okay.
So this quartic is down in the 1 over n.
It's down in 1 upon n in the limit when GS is held fixed. Okay.
So if you've done the same calculation for a harmonic oscillator, not an inverted harmonic oscillator, where the Fermi surface would be like a circle, a disk perhaps, then you have some phi naught around that.
Absolutely.
Then you would not encounter.
I don't think so. And that, of course, is hard to interpret really in string theory in this sense because there's no limit where the discreteness of the spectrum goes.
Yeah, I guess this LLM geometry is.
LLM geometry is okay.
That is more relevant.
That's right. Yeah. We will actually work in a limit.
There's a question.
Yes, please.
So this n is taken. So n is still large enough that we don't have to worry about the eigenvalue being discrete.
Yes. So I'm taking n to be large enough and GS to be small. Okay. Such that this thing I hold fixed.
Yes.
So that's a kind of a limit where I can still use the Thomas Fermi approximation. Okay. This is away from the double scaling limit, but we are analyzing the problem in this. Okay. We think in your mind n as 10 million, take GS to be very small. So this product is orthogonal. Good. Very good. So how do we solve the problem? Just a few slides about that. So as I said, we'll have to think of this as a quantum quench in which you start off with some initial configuration which is not the ground state of your problem and then you evolve it in time. So let's start off with a Fermi surface which is given by this Heaviside theta function. If it were the ground state, this extra term would not be there and it would remain like that. So that would be the time-independent ground state of this problem in the presence of this X4. But because of this, it is out of equilibrium, and different points on the surface have different energies, and therefore different time periods. It's like they're like two wells. Consider just one such well. The time period depends on the energy. Okay? Nevertheless, this is a phase space density. There should be a U here. Its time evolution is given by a Liouville equation. Okay. Now, Liouville equation, the solutions are area preserving maps. So, the phase space density at a point X, P, and T is given by the initial density translated backward in time. Okay. So you want to find the U at some X and P, you see where that point came from. Okay. And so this is immediately a solution of this equation. So we already solved the problem. So if you want, these are explicit solutions for the quartic potential in terms of elliptic functions. Nothing very useful, but the picture does. Yeah.
Solving for the actual motion, even of a single particle with that quartic, is non-trivial, right? I mean, you reduce it to some quadrations or something. And
yeah. These integrals can be done in terms of the elliptic functions.
Okay. So then you just, yes.
And then you just ask mathematics. That's what we do.
Okay, good. Got it.
Good. So, here is a picture of the time-dependent Fermi surfaces for r less than 1. Yeah. So now we have periodic orbits because the potential is like this. So things are moving like that. So all the instant snapshots of these Fermi surfaces are like closed loops. The green one is what you started out with, and this orange one here is at some time t equal to 7. Okay, I have also drawn on this picture 2 other orbits, which is the orbit of the particle with minimum energy in the Fermi sea and the one with the maximum energy of the Fermi sea. Okay, so as I said, different orbits have different energies. So there's one which has a minimum energy and one has a maximum energy, and I've drawn those things. The Fermi surface is in this particular case is bounded by this green line at time t equal to -5, and the orange one is at t equal to 7. Good. If you zoom in on the region far from this infrared wall, they look pretty much, like what we had for the inverted oscillator potential. And that, of course, is not a big deal. This is a picture at early times.
Say this last thing again. Sorry.
The last thing is that if I zoom in on this part of this picture, the part of the picture which is close to this region, okay, then the picture looks like the previous pictures which I just showed.
But this is a plot of x versus p, right?
This is x versus p.
And by your definition, that x equal to 1 or whatever is.
Yeah, x equal to 1.
Okay, yeah, I'm with you.
Right? Okay.
Why is there a
Yes.
Go ahead.
why was there a maximum and a minimum?
Because it's not a harmonic oscillator. So the time period depends on the energy. Okay. So in the Fermi sea, not the Fermi sea, among all the points on the Fermi surface, each point would have different energies. Right? So there would be one which has the smallest and one which has the largest. These are orbits of particles which are on the Fermi surface. That makes sense?
Or have you go all the way to? Okay, so the reason is because it is closed, and hence you have a two energy differences. If the orbit were to go all the way to infinity, then the energy range would be unbounded. But since the orbit is kind of closed, you'll have a minimum and a maximum. Is that
right? Or if you think about it, if this was an equilibrium solution, there will be just one orbit. Okay, the Fermi surface, all the points on the Fermi surface would have the same energy. That's equilibrium.
If there was no to the power r term, then all the.
That's right. If there was no such time, you didn't turn on a non-trivial excitation. But now we have deformed the initial Fermi surface. So that means the points on the Fermi, what I am calling the time-dependent Fermi surface, which I explained, they all have different energies. They have different energies, they have different time periods. So I have drawn the ones with the maximum and the minimum, and the little thought tells you that the Fermi surface itself will always lie between them. So this is good. At early times, it looks like what is started out with in the double scaling way. So let's see, but we're interested in what happens at late times. So late times, two things happen. The first things happen is this feature that what I called a quadratic Fermi surface, namely at a given x, there are precisely two values of p that fades. A fold on the Fermi surface appears, and folds also appear in water waves, but they are non-linearities which actually cure that fold. Waves break. In this case, there's nothing to break. The reason why a fold on the Fermi surface would appear is that if I take a particle above the equilibrium Fermi surface, the higher it is, the speed at which it moves is higher. del E del P is P, roughly speaking, because E is P squared. So as a result, as time goes on, this thing keeps going on. And at very late time, this thing keeps folding onto itself in a way that it sort of basically fills the allowed phase space region, namely the region between the minimum energy orbit and the maximum energy orbit. Of course, each point has that energy is conserved. They're moving at the thing, but the surface is getting folded up, and so we have to understand what that.
It's also developing some oscillatory regions.
It's not oscillatory. This is mathematical.
Okay.
It's actually a continuous thing that just goes.
Yeah, I was wondering whether there's some.
There's no break.
Okay.
There's no.
To worry about reaching someone first time or something where the scale of the fluctuation starts approaching H bombs. That's probably very, very late times from Tommy.
It may not be. It may not be actually.
Okay.
So you can estimate when this thing happens. Of course, for this thing to happen, the fermion has to go to the wall and come back. You can estimate that time. This time is actually log of n.
Okay.
And if you estimate the time which takes to that fold to wind around, it turns out to be log of n whole square.
Just you told that these surfaces can have folds, but can these also cross somewhere? Is it possible?
I don't think they can cross.
You can't cross.
Yeah, I don't think they can cross. Yeah.
And what's the reason?
Because a crossing would mean that what would a crossing mean?
Picture of all the separate blocks.
Right. Because the fermions themselves are moving in some closed orbit. They do whatever they do. I have to think about that. I think it means something.
Maybe I can make a comment here. So
Okay.
if you think of fermions in a box, like a periodic box, then whatever fermion, let's say we consider two fermions with momenta P1 and P2. If P1 is greater than P2, whatever the dynamics is, this order is kept.
Right. Okay.
So whichever is the higher momentum, it just moves around in the same constant momentum line. And so P1.
In this case, the energy, I guess.
Yeah, here it would be energy.
Energy, yeah.
As a result, the energy is the ordering of the energy is preserved.
Yeah. Okay. Good. Thank you.
So I didn't fully understand the fold. So you're saying earlier for any x you had two p's on the Fermi surface, and now you have multiple more than two p's as a g because of this quadratic term.
Well, no. It can also happen in states for the inverted oscillator. Nothing to do with that. It's a state. I'll come to the meaning of that. We have an interpretation.
Yeah.
Okay. When r is greater than 1, something very similar happens. And as you can see, the green one is what we started out with. First, it starts moving bodily, and then this thing folds and, fills that entire. So for both these regimes, the late time Fermi surface folds onto itself into a large number of times, forming a kind of a space filling curve between the lowest and the highest energy trajectories. Yes. And the time scale for a fold to appear is given by the period of the lowest energy orbit, and that happens to be order log of n. So what do folds on the Fermi surface mean? So here is an interpretation of the folds meaning. So let's forget everything about non-relativistic fermions, which are very complicated. Let's do things which we love. Chiral fermions in 1+1 dimension. Okay. Chiral fermions, Mandelstam tells you how to bosonize that fermion. So this I'll call psi dagger, the right moving fermions in this case, and this is the chiral field, which the derivative I'll call alpha, and alpha is psi dagger psi, And the Mandelstam relations also tell you what the momentum density is like. You can calculate what this is the momentum density in terms of the fermions, and this is the normal ordered object of the alpha x whole square. It's like T plus if you wish. Okay, so these are exact. So let's consider what do they mean in the Thomas Fermi approximation. In phase space, the Fermi sea is now an infinite Dirac sea because we're doing relativistic fermions. So that's actually very simple. A state with no folds on the surface can be now characterized by a single function of that position, just P of x. And those relationships applied to Thomas Fermi tells you that the density of fermions is just basically P, that we know from the usual bosonization formula, and this is pi del x phi, that's a typo here. But basically the momentum density is alpha squared normal ordered, and that's V squared. So this kind of state is like a coherent state where the dispersion of alpha vanishes. Now let's see what happens when...
What was alpha again? Just
derivative of phi.
It is a...
Okay. B plus of phi. We didn't kind of think so. It's like B plus of phi. So what happens when you have a fold? So here is a simple example of a fold. The Dirac sea goes all the way down. So it goes at P plus, P1 plus, P1 minus, P2 plus, and then all the way down. So you can calculate these two objects, and these are given by those expressions. And of course, what this means is that this object is non-zero. Okay? So what is happening is that this means that the state has large quantum fluctuations of the bosonic fields. And the large quantum fluctuations have like order 1 upon h bar quanta. So they survive in the Thomas Fermi limit. So the state is becoming very quantum in terms of the bosonic field. And that's expected because we already saw in our setup, this is just a general kinematic connection. In our setup, we saw that at late times when these things start happening, the couplings also become very large. So it's not unexpected that quantum fluctuations are very large.
Is it to say that there's a sort of approximation that usually goes with the Thomas Fermi picture, right? Is it to say that approximation is getting bad because you're cubic and other corrections?
No, quite the contrary. The Thomas Fermi, and this is one of the things I think Gautam has emphasized in many papers. It's the Thomas Fermi in terms of the phase space density remains a good description. If you want to replace it by a single classical bosonic field, that breaks down. And that breaking down is given by the fact that the fluctuations are becoming large. Good. So what is the final state? So we state that, so I should say that I did it for a chiral fermion. Now in a chiral fermion, you can start with a state which corresponds for a fold, but it can never happen that a state with no folds develops a fold. It's because the dispersion relation is linear and the phase space velocity is equal to the group velocities. It is not that things high up move faster than the phase below. Okay? But you can have a state which is like this. For non-relativistic bosons, you can find non-relativistic fermions, you can show that in generic states, this thing can happen. There's some conditions which actually I and Sumit did in a rather different context of when this kind of thing can happen. Good. So we wanted to understand the late time behavior, and I'll come back to my the time-dependent solutions. We want to analyze what happens at late times. And in this problem, we found it convenient to go to action angle variables. The reason is that we can use this nice paper of Kulkarni, Gautam, Takeshi, Morita, who among many examples, they studied the problem of free fermions in a periodic box, okay, where the x goes as pt plus a constant, and that's how in a generic integrable system, action angle where angles grow linearly with time, so we can basically use whatever they did to analyze this problem. Yeah. If you want, this is what the action angle variables are, like it or not. So let me draw it in terms of pictures.
Say this in front of such a reader. Is this the first time action angle variables have been used for something useful? Sorry, you learned it in Goldstein only. Okay, never mind. Good.
I think this is the first time I have used it in my research. I mean, we were thinking about it, and I was talking to Gautam, like it's how to do this, and then we figured out that, of course, it has to be action angle variables, and that's the way Hamilton solved problems. Right? Okay. Hamilton actually solved problems. So it's not just the mathematician showing proofs. Okay. Actually, Poincaré. Correct.
Just a question, sorry. The action is tied in reversal symmetry, is it? Or not?
This object J.
The thing that you wrote.
Oh, the action which I wrote. Yeah.
Is it? The reason.
No, there's an.
So
what do you mean? The state is not time reversal symmetric.
Yeah. So a state.
Dynamics is. Yeah.
Yeah. You said a state with no fold will not evolve into a state with folds.
If it were relativistic fermions.
Yeah. But can a state with fold evolve into a state with no fold?
No, because then you could run it the other way around and you'd be.
No, but that's why I was asking, is it symmetric?
Yeah. This is normal free massless fermions.
Okay.
Yeah. But relativistic fermions, both things can happen. Okay. So let me explain why these are useful. So the big deal about, what is the big deal about action angle variables? The big deal is that you find variables in phase space such that whatever takes the place of a space coordinate is an angle, and that angle changes linearly in time. That's a nice thing about this thing. That's why you reduce the problem to that of quadratures. So this is how this action, the angle goes linearly in time. This angular velocity is the derivative of the Hamiltonian with respect to the action. That's one of the Hamilton's equations of motion. So if theta was just the entire real line, just like an usual x, then if I started out with some Fermi surface, which is some product of theta functions, the Heaviside theta functions, you just replace the arguments in there by sticking in, instead of theta of t. That's all you do. Of course, theta is an angular variable. So you cannot do that. You have to maintain the periodicity in theta. And so this is what Gautam and collaborators did. They realized, okay, we just make it like that by summing over images. So this is the sum over images, which maintains the periodic nature of the variable theta. So this is the full solution to the problem. Whatever your initial profile is, this is the profile at time t. Let me explain what the initial profile, what are the objects in this initial profile are. This capital theta is a Heaviside theta function. Okay? In this picture, this violet thing is the initial Fermi surface. Okay? Everything inside is filled. The action is a function only of the energy. So equal action lines are equal energy lines. So what I do is I draw a line of constant energy, which also means action is constant, given by the relationship between the action and the energy. And this intersects, the angle is really like an angle in this picture. this intersects this Fermi surface at 2 points, which I call theta 0 plus and theta 0 minus. So the first theta function tells you that when this theta plus 2 pi m is, imagine this at t equal to 0. So this term is not there. So that's the initial surface. So then theta plus 2 pi m less than theta 0 plus is going to be the filled orbits, the filled fermions, and bigger than theta minus is going to be filled. Everything outside is 0. So that's the initial thing, and it evolves the way I just showed. I mean, it evolves according to the equations of motion. Okay. So then you use a trick to analyze what this looks like. This trick is a Poisson reformation formula, which expresses a sum in terms of a sum and an integral, which is given by this formula. And you rewrite, using this, you rewrite what is the phase space density at some given time t. And this looks like this. K is an integer. And the first thing you realize is that I have separated the k equal to 0 term in this. This part is completely independent of time. Okay? And the time dependence is in this horrible sum. But at late times, let's say how does the time appears in the time dependent? It appears in these omega times t. And there is an I times k sitting outside. So it's a highly oscillatory thing. It sort of oscillates very, very rapidly at large times. So you would expect that there will be dephasing. And at very, very late times, this thing will not contribute. So the next touch is to estimate how does that happen as a function of time, and that's the final part of the story. So let's remind, what does this picture look like at late times? It's like a space-filling curve between the points of minimum and maximum energies. Okay? So this cries out for a coarse graining. Okay? So what you do is you coarse grain the original phase space density with a kernel with some width sigma, and the coarse graining should be over energy. It's like coarse graining in this direction. You know, in this picture, this is the angle and that's the energy, if you wish, the energy direction. So you coarse grain in energy windows, which are determined by sigma, to sort of average those things out into some smooth distribution. Okay? And that paper of Gautam had a very heroic, sort of calculation of how, in a different context, but so we just lifted that analysis. And what you find at the end of the day, I don't want to go through the details, at times which are much, much bigger than the coarse graining scale or the inverse coarse graining width in the energy space, these time-dependent terms fall off as a power law in time. In this case, the power law happens to be half. Okay? So the conclusion is that this coarse-grained quantity, therefore, approaches a generalized Gibbs ensemble. It cannot become a Gibbs ensemble because it's an integrable system. And if you look at what is this object, let's go back this slide. This object is the time-independent part is the difference between this point and that point. Okay? And so what is that object? This is actually the total number of fermions of a given energy, which is determined by J. Integrability of the system tells you the number of fermions at a given energy is going to be conserved, right? And so this coarse-grained object is precisely that. Okay?
I'm losing the picture, but let me ask you the following two. So you have things moving, free fermions moving in this quadratic plus quartic trap.
Right.
And then you have some minimum energy in terms of your initial state, some minimum energy fermion and some maximum energy fermion. And is the final picture that you, in a sense, fill out subject to, I don't know, the Gibbs generalized ensemble? I'm not sure. But what is the final picture? You just fill out between the minimum and maximum?
You fill out by intervals of 0 and 1. Let's draw the picture in the canonical state where I put J and theta. This is nice. So it's sort of like this. So this is a minimum energy surface and that's a maximum energy surface. The field region of Fermi surface is sort of like this. If you take something like this. This is filled.
And what decides the gap between the filled and unfilled? Something?
I think it just becomes a space filling thing. I mean, it's really like a cluster.
You just fill in.
Yeah, except that now when you are doing this averaging with a kernel, the object which you get is not strictly between 0 and 1. It sort of smoothly interpolates.
Something that smoothly, some equation tells you how to interpolate between.
Exactly.
So you get some smooth density between the maximum and
absolutely. Right.
And all thetas are sort of does the density vary also with theta? That's smooth? No,
it doesn't.
It doesn't.
It doesn't.
Okay. So with J.
But then you wouldn't have an equilibrium.
Okay, got it. Yes. Okay.
Very good.
Sorry, can I ask a question about this first point? Why do you need this behavior T greater than 1 by sigma? Like in the Gautam's paper, there was no energy window. Still, you get some alpha there also.
Yeah, so in the Gautam paper, I think maybe Gautam should answer this. So there the integral was over all momenta. So they were looking at the fermion density. Am I right, Gautam?
Yeah.
Gautam is gone.
Yeah.
Right.
Yes,
But here we do a little bit different. We actually coarse-grained, we actually average over an energy window, right? And so the average of the energy window, you have to have this comes from the analysis of the dephasing. So if you look at this expression, I didn't show what this, yeah. So you take this entire expression and then you integrate over J, actually omega, and then do this integral. Once you do this integral, there are two time scales. One is the scale which is given by 1 upon sigma of the thing you are multiplying the energy is, and the other is the scale which is the time. And then you look at what is the time regime where this dephasing actually happens, and that is the time. Okay, does it make sense?
Yeah, thank you.
The reason why you're going to the angular coordinates is because you don't want folds in your phase space?
No. There are folds,
Yes.
even in angular folds. Yeah, it's because theta by angular coordinates, the theta at T is omega, and it's very easy to implement. It's easy to. I mean, you don't need to do that probably, but
Okay.
we basically wanted to lift their results.
One last thing. I mean, this fancy action angle variables, is it to implement some kind of a generalized Gibbs ensemble in a more natural way?
Yes, exactly.
Otherwise, sanity would say, okay, you have some constraints, minimum, maximum energy, fill it out. Like,
Right.
okay.
It sort of
Got you.
makes that accurate.
Makes that
very precise,
Okay.
what the generalized results are. Okay, so let me finish. What does it mean for string theory? Actually, I don't know what it means for string theory.
Sorry, before that, I thought you were coming to the punchline. So now what happens? You hit that wall, that space like singularity, and then what happens? What happens to the tachyons as they...
I think that picture is gone because we have gone too late in time to ignore that wall.
So therefore, space-time as such is no longer...
Yeah, I think something is happening to space-time, and it is becoming grainy in some sense, right? In a precise sense, I don't know.
But it's not as if you wait long enough, again space-time emerges, nothing.
No. This is you wait very, very long enough, order of log of n, right? And then you sort of get the space density, which is now a nice function. Okay, and then whether that has a space-time interpretation in some natural way, I don't know. But it's something, it doesn't go berserk. That's what I'm trying to say.
But not in the original variable.
Yeah.
Not in the 5.
Not in the 5 variable. The 5 variable has failed long time ago, actually. Right.
And the quantum fluctuations in this description are small. Right?
Yes, I think in this description, their quantum fluctuations are small.
But were they big to begin with? In this description, no, right? Presumably, or am I wrong?
In this description?
Yeah.
No, I think they're all controlled. Yeah.
So, can you, did we need the original description to set up a space-time interpretation? Just asking.
So,
I don't understand.
what did you mean by that?
What I meant was that, okay, I'm sorry I haven't understood it so well, but in terms of your phase space, then you had some density phi, and didn't you be able to get some notion of things moving on the light cone of space-time and so on with small corrections, right?
Right.
And now when the corrections become big, that's not very useful, etc.
So that is what. So at early times, that's all very good.
That's all very good. But
Right.
you go forward, it becomes
Right.
okay. But now, could we have tried to construct the early time description in terms of these variables? No.
Then you'll go back to whatever you had. At early times, nothing special would happen.
But now if we continue using these variables, and at late time there is no nice light cone or anything.
I don't know.
You know, not in any obvious way.
Yeah, not in any obvious way.
This fermion description, does it have a natural way to think about it in the bulk?
These are D brains. These are unstable D brains.
So at early time,
It's like
when phi was a good variable, was there a way to say all of that alternately in terms of?
so. The way I see it, that early times, thinking of these D brains in the closed string language was very natural and nice. Okay. At late times, somehow I don't know really what happens.
But maybe we should just ask about a D brain instead of saying send a tachyon in. Suppose I send a D brain in, which also I could do.
Yes.
Okay, there's a wall. If the wall was subluminal, it would hit the wall and come back or something. I'm not sure. Now it's superluminal, so the D brain goes along and hits this space-like wall too. And then what happens? Is that easier because we can track a fermion more naturally?
So the thing is that by the time that happens, it's hitting the space-like thing, that fermion actually gone back to the infrared wall and turned around.
Infrared is what now? I mean, what is
the non-linearity of the potential.
the non-linearity of the potential? Okay, I see. It's gone back and turned around.
Yes.
Okay, yeah, then that's one.
So I think in terms of D brains or fermions, everything is normal. Nothing funny. I think the question is about, is there a closed string meaning of that? And if so, what? But I tell you why there would be a little bit problematic thinking about a closed string meaning is because all this can only happen if I don't stay in the double scale limit. Now recall a double scale limit is continuum worldsheet. So this would be kind of a discrete worldsheet, and what would be a space-time meaning of a discrete worldsheet? I mean, I don't know, something I think I would like to understand. I just threw it out that
going away from the double scaling limit, does it mean doing at finite time?
It's only doing finite GS times N.
Finite GS times.
Yeah.
But I'm taking away the following lesson, you can correct me, that the collective boson description It's a little bit like this discussion we now have, whether the bulk description is correct or not. We all know the n equals 4 is correct, right? And a little bit, aren't you saying, look, the bosonized description, it has all these caveats and so on. But of course, the fermion description is great, right? Always great. Free fermion.
Yeah, of course.
But is there no way to phrase, I agree, the question is intrinsically a bulk, quote unquote, closed string theory question. You're hitting this wall, but can't we phrase a question about the outcome in terms of fermions in some way?
I mean, you're happy to stay with fermions, you can happily stay with fermions.
I mean, is there a way to ask the question, if I sent the fermion into that space-like singularity, what would happen? Or is there no way to ask it since?
It's going to turn back before that happens.
It's going to turn back before that happens.
Yes.
So then I would say any probe of fermions never sees the wall. The wall is a figment of the closed string description.
You mean the Liouville one? That strong, this space-like thing? Yeah. So that is this thing is actually an artifact of the double scale limit. I mean, there is, that's my interpretation, there is no such thing.
So I think, sorry, but please, you should conclude. I think what you're saying is if you had a fermion, it would, go and hit the other part of the wall because there's a quartic potential, and come back nicely and hit this wall again, and so on and so forth.
And it becomes very complicated. It mixes in phase space. There is a mixing in phase space, which sometimes everything is normal, I think.
And if the region close to the inverted part has some nice, smooth space-time description, then can we say that, okay, look, we started close to that, then the fermions started moving away, the collective field theory got bad or at least uncontrolled, but fine, we tracked the fermion, and after a while it came back, and therefore but
then you realize that even near the hump of the potential, your closed string interpretation has changed.
Right, it has changed, but there's a new closed string, and I could have connected the old to the new through the fermion language. Can I do something like that?
So I think that's a question. Can I use this coarse-grained U which you got to have a new coarse-grained boson, which has some normal dynamics?
Right. And then that would be great, right? I mean, so you have an initial question phrased in terms of closed strings. We translate to fermions. Then we follow in fermions, and we translate into whatever are the correct closed string variables in the future.
It may or may not happen. I mean, I don't know. And the reason is that we do know that the discreteness on the worldsheet remains. There has to be a signature of that in target space.
But you have this effective theory of fluctuations for the density around any given background phi naught.
Right.
That was you had the general formulas, and then you derived a metric from that.
Right.
What would something go wrong with that metric if you chose that phi naught? Coarse-grained?
Well, nothing. Okay, so that entire thing was predicated on the assumption that the fluctuations are small and the couplings are weak.
Yes.
It's an intrinsically sort of perturbative description.
Yeah, but I was wondering whether there are some new fluctuations around this coarse-grained.
Could be. I mean, you might start with this coarse-grained U. I mean, that's what I would like to understand. You can start with this coarse-grained U and define a phi and a phi and see whether that has some nice dynamics.
Something very bad about it.
Yeah.
Because, in the LLM context, if you try to do that, something very bad happens.
I sort of suspect that it wouldn't be that straightforward because of the fact that if it did happen, I would imagine there would be a worldsheet description as well. Now I'm bringing in the string theory part of it, that there would be a nice, continuum worldsheet description of it. And that is not going to happen here because the discreteness of the worldsheet sort of remains. Okay. Now there are these other ways of thinking about the closed open discretity, particularly for the matrix integrals, where there is actually a string theory even away from scaling limits. Maybe something like that happens. I mean, I'm not quite sure.
Yeah. One more thing. I mean, sorry, I followed the details of the last part very poorly, but are you saying because the late time state is some equilibrium state of this generalized Gibbs ensemble, right? So are you saying that, look, if you started with all the air molecules, so to say, in one corner of the room, I had some nice space-time description. Then it equilibrated, and as far as we can tell, there's no nice space-time interpretation. Roughly, the equilibrium state is not so clear, has a space-time.
You're not very clear. I don't know what happens. I mean, there is an equilibrium distribution.
But even so, at least on the Poincare recurrence time, again, all the air molecules will be on one side, and you'll get back. I mean, if I'm willing to wait e to the n, at least you'll recover space.
E to the n, probably that will.
So at least from e to the n, you'll be able to ask it.
Probably, yeah.
Okay, it's not satisfactory, but at least there it seems, right? The question is whether at log n times.
That is the point, That's it. Anyway, I'll finish with that. I think maybe there's something to think about.
At log n times, so the evolution of the phase space density always happened by the classical equations of motion?
Yes.
Do I have to worry about, so these equations also have quantum corrections, right? Like this Moyar corrections and so on.
Yeah.
These don't become important at log n time?
Not if GS is small enough and N is large enough. For generic GS and N, of course, I mean, you have to take phase space density is not 0 and 1. U squared is not U star U is
Exactly.
Right.
So the effective H bar here is what? Is G string.
G string. So I think Spenta and Gautam and Avinash just set up a quantum analog of that. I mean, I don't know, Gautam will know a little better. Whether it would be interesting to see when that kicks in.
The higher G string.
I mean, the full quantum nature of the fermions.
But I mean, let me ask one thing. I mean, isn't the moral here that the fermions are always correct and the pure string description is
yes, I think n equal to 4 is always correct.
And the other one is suspect. But I mean, you're saying more than that.
There may be a way of have a space-time interpretation of the late-time physics.
But only in between, it seems almost certain.
Yeah, that's right. In between, it seems very bad, but there may be.
Is there a bulk interpretation? I think you asked this question. Is there a bulk interpretation of the space density, even at small time, even in some coarse-grained fields? Because that seems like the correct field to use.
Right. So the phase space density, of course, its moments are bulk interpretations because it's like is integral over P is the bosonic field. So I think those are space-time interpretations. Yeah. I mean, if you think about the non-commutative, if you consider X and P as non-commutative variables, but that's like restating the problem. It's not a non-commutative space is not really space. Okay, very good. Thank you.